In this video, we get to add to all the work that we've done recently on trigonometric integrals by introducing the idea of a trigonometric substitution. Now, the difference between this problem is that we're going to be given integrals that don't have any trig functions in them, but based on what we see in those integrals, we're going to have to use certain trigonometric functions and identities in order to simplify the problem, right? So what are these functions? What are the clues that we're going to look for? Well, we are going to be interested in integrals that involve the following radicals, right? So integrals involving the following radicals, right? So integrals that are of this form, let's say the square root of a squared minus x squared, and the square root of x squared plus a squared, and the square root of x squared minus a squared, right? And here the assumption is that a is a positive constant, right? Right. So the idea is integrals that have these radicals, right, may be evaluated using specific trigonometric substitutions. Right? So first let's address why. Like, why do we need trig functions when we don't see anything that's remotely related to trigonometry here, right? Well, first of all, that's not true. In fact, there's a lot that we can see. There are certain patterns in these radicals that will actually lead us to trig functions. But the problem is, under the square root right here, we have the difference of two squares, and here we have the difference of two squares, and here we have the sum of two squares. But none of those expressions under the square root are perfect squares. So it makes it very difficult for us to evaluate or simplify the integral as it is, right? And if there is no apparent substitution that we can use, then what are we left with, right? So the idea of using a trigonometric substitution is so that we will end up with a perfect square under the radical, and then the integrand can be simplified, right? So we're going to make a special trigonometric substitution for each of these forms, and we're going to end up being able to simplify our radical, right? Now, before we talk about what those substitutions are, let's just make a few assumptions, right? And in fact, we made the main one right here, is that our a is going to be greater than or equal to 0, right? And obviously that's going to be a constant. So let's take a look at these three integrands and see what we can make of it. Now, if you think back to, let's say, either geometry or trigonometry that involved right triangles, expressions like these came up all the time. And depending on which side of the right triangle you were finding, you would have ended up with one of these three radicals. So what I can do is I can actually give you a visualization of where this type of radical will come from, and what this type of radical will come from, and similarly this type of radical, right? So let's start with the first one. Now, here is the right triangle that is often associated with this type of expression. If you think of the Pythagorean theorem, whenever you have an a squared minus something squared, that usually means you're finding one of the two shorter sides, right? And that's because of the difference, right? So for instance, if I label my hypotenuse with A, and if I call this my theta, and if I label the opposite side here as x, right? Then if I say, well, what is the length of the missing side, right? Then I would take my hypotenuse squared minus my opposite squared, and then I would have to take the square root of that. And I would end up with this very same expression, right? So basically, this type of right triangle, it gives me a way of introducing a trigonometric ratio, right, where one of the sides is exactly the radical that we have right here. So for instance, if I wanted to find now a relationship between this angle theta, the hypotenuse, and the adjacent, the opposite, then I could use the sine function, right? So for instance, if I say, what is the sine of theta? Then the sine of theta is your opposite over the hypotenuse. So it's x over a. So then what I can do is I can solve this equation for x, and I get the equation x equals a sine theta. So basically, if I use this equation, whenever I see a radical of this form, it will allow me, along with some trig identities, which we will state earlier, and we've used these in recent videos, it will allow me to get a perfect square under the square root, and then the problem can be simplified. So we're going to use this equation to switch from x to theta and follow our substitution process, right? So basically, for each of these radicals, right, we will have an equation of this form, but the equation involves a trigonometric function. So we're going to be turning an algebraic integral into a trigonometric integral, which is why we did the previous section, so that we know how to handle certain types of trigonometric integrals, right? Okay, so let's see if we can repeat this process for the remaining two forms. Well, this expression is what shows up in the Pythagorean theorem when you're finding the hypotenuse. You would square the two shorter sides, those lengths, add them together, and then take a square root. So I could draw, I can draw a right triangle that helps us visualize where an expression like this would come from. So again, if I call this my theta, and now if I put my a here and my x there, then if I were to ask you to find the length of the hypotenuse, then you would square your x, square your a, add them, and take a square root. So we will end up with a squared plus x squared, right? Or x squared plus a squared. It doesn't matter. In this particular form, addition is commutative, so it doesn't matter if you have a squared plus x squared or if you have x squared plus a squared under the square root, right? Now let's see if we can find a relationship between, again, the angle there and this x and this a. So the ratio would have to involve the opposite side and the adjacent side. That sounds like tangent. And in fact, if I say, well, what is the tangent of my angle theta? Well, that's x over a. So in this case, whenever I have a radical of this particular form, then this equation, x equals a tangent theta, is going to give me a way of simplifying this expression so that it becomes a perfect square, right? All right, so we got 2 out of the 3. The third one, again, let's see if we can draw a right triangle, right, that will capture or somehow produce this as one of the 3 lengths. Well, in this case, again, with the difference, it means I will be finding one of the two shorter sides, which means x would have to be my hypotenuse. So I can put that there. And in principle, it doesn't really matter where I put the a, but again, to be consistent with like the one that came before, I'm going to put my a there. And again, if I ask you to write down the expression that gives the length of this third side of the triangle, and these are all right triangles, by the way, right? Then this missing side has length that's given by the square root of x squared minus a squared. And again, let's find the ratio that relates theta, a, and x. Well, so this would be the adjacent side. That's the hypotenuse. So sounds like cosine to me. So if I say, well, the cosine of theta is a over x. And if we follow suit with the other three, let's solve this for x. So multiply both sides by x, divide both sides by cosine theta. So I have x is a over cosine theta. And that's okay, but 1 over cosine we know is secant, right? So let me write one more equation here, and then x is equal to a secant theta. So there are the three kind of fundamental or basic equations that are used in these trigonometric substitutions, right? So it's not, in this case, the nice thing is there isn't really any guesswork as to, okay, what substitution do I use? You recognize this sort of expression, right? With no other method apparent, if there is no basic u sub that will work, then we're going to attempt to use this equation as a way of converting our integral to a trig integral. If we have a square root of a squared plus a squared, then this is the equation that we will use. And then similarly, if we have the square root of x squared minus a squared, then this is the equation that we're going to use for our trig substitutions. All right. Okay, so let's now the one other assumption that we will make is that, and it seems like a reasonable assumption given the triangles that were drawn, we're going to assume that our theta is in the interval 0 to 2 pi. I'm sorry, 0 to pi over 2. So we're going to assume that our theta is an acute angle, right? And I mean, at least it's consistent with our right triangle, right? So we're going to make a little assumption here, right? This assumption can be dropped. It just makes some questions a little bit trickier to deal with. So we're going to work with questions where our theta is always between 0 and pi over 2, right? So theta is acute, which means this. So that means all our ratios are positive. And again, it kind of makes sense since we're using this sort of right triangle to get the relationships between the theta and our x. All right. Okay, so you got to look at some examples here. Let's take a look at our first example. And let's start with an indefinite integral. Right, and here is our problem. So it's the square root of the quantity x squared minus 25, all divided by x, and we have to find that antiderivative, right? And again, as much as we would like to be able to do it, x squared minus 25 is not a perfect square. It is a difference between two squares. So we can't just take the square root of the x squared and the square root of the 25. If we could do that, then this whole process would not be needed, right? Okay, so based on the form, it looks like it's the third case right here, right? So we can see the square root of x squared minus 25. So basically, it matches this particular form with a squared equals 25. And with the earlier assumption that our a, in fact, let me go ahead and rewrite that assumption here, that a is positive, then it means that a is the square root of 25, which is 5. So the equation that I need to convert this into a corresponding trigonometric integral is x equals 5 secant theta, right? And as with every substitution that we've done, we are going to convert the integrand, and we also have to convert the differential. So I need to figure out what dx is, and I need to figure out what this integrand is in terms of theta. So there are two key things that we have to do right at the start. The dx is very consistent with how we've done all substitutions up to this point. We have an equation, x equals, if we want to figure out what dx is, we take a derivative. So find the differential form of this. So dx is 5, and the derivative of secant is secant theta tangent theta, and then it's that differential. So take the d theta over, right? So at the start, it's going to look really messy because what we're going to do is we're going to replace this with that, right? But that's what we have to do because we can't ignore the differential. You ignore the differential and this whole process falls apart, right? So we have what the dx is. Next, we need to figure out what this square root of x squared minus 25 over x is in terms of theta. So let's do a bit of side work. In fact, most of the work that you do in these problems is kind of off to the side. It's more trig and algebra with a little bit of calculus sprinkled in, right? So let's take a look at just this part, just the integrand, right? So we have that over x. Well, the nice thing is this process tells us what x is. So wherever there is an x in this integrand, we're going to replace it with 5 secant theta. And then we're going to work and work and work and convert it in to make it as simple as possible because that's what we're going to have to end up integrating, right? So let's start with we have the square root. Now it says x squared. If I square 5 secant theta, I will get 25 secant squared theta. And then I have a minus 25 there, and that's all under the square root, right? And I still have a difference of 2 squares. That hasn't changed, but it will in a bit. And then I have to put that all over 5 secant theta, right? Now, under the square root, I notice there's now a common factor of 25. So let's take out that 25. And what we're left with is secant squared theta minus 1. And we still have the 5 secant theta there. But secant squared theta minus 1, we use that quite a bit in the sections where we looked at the integral of powers of tangent and secant. Secant squared minus 1 is tangent squared. So I can replace what's in the parentheses with tangent squared. And what that does now is I have a perfect square under the square root, right? So we have this, and then we have our 5 secant theta, all right? Okay, so now this is a perfect square. In fact, let's write that, and that's what we want to see. Just like in those arc length integrals, we're glad when we recognize that this is a perfect square. Same thing in this case. right? Because without a perfect square, the radical doesn't go away, right? So when we take the square root of 25 tangent squared, that gives us 5 times tangent theta, and then at the bottom here I have 5 secant theta. All right. Now, if we so we look at this, and obviously the 5 can be canceled out, right? So we're left with just tangent theta divided by secant theta. But tangent divided by secant, that might be, we might be able to simplify that, but because there's a dx that we're now going to have to account for, I'm going to leave it in this form, and then I'm going to take what we have here, multiply it by my dx, and then simplify all of this, right? Right. The big thing that I wanted to accomplish with this step here is to get rid of the radical, which we did, right? So no square roots here. But we still have to keep in mind what's going to happen with this dx. So now let's write another line. So we have this over x now times dx, all right? Well, look at what we have. We have the integrand in terms of theta. We have the differential in terms of theta and d theta. So replace the square root of x squared minus 25 over x. Replace that with the tangent theta over secant theta. So let's write that. And then replace the dx with this other differential, the 5 secant theta tangent theta d theta, right? So what do we end up with here? Look, the secant completely goes away, right? So the secant goes away. We have a constant of 5, right? And then we have tangent times tangent. So with this trigonometric substitution, this integral, right, reduces to something like this: 5 times tangent squared d theta. All right, so now let's write it down. And again, this is the thing I always emphasize: write down where we started. So we have this dx, and through, let me write a longer equal sign. So by using this substitution, by letting x be equal to 5 secant theta, this indefinite integral turns into this indefinite integral, 5 tangent squared theta d theta, right? And now what happens is our mindset switches. It now switches, okay, now I have to know how to integrate, some trigonometric function. And I have to think about identities. And I have to think about, whether I have to use half-angle identities or Pythagorean identities. Well, a Pythagorean identity will help us here. In fact, the same substitution that we used to replace secant squared minus 1 with tangent squared, using that same identity in reverse will give us a relatively easy solution for this problem. So I have 5 times the quantity secant squared theta minus 1 d theta. If I factor out the 5, and now the antiderivative of secant squared is finally one of our basic ones. Antiderivative of secant squared is tangent theta, and the antiderivative of 1 is theta. So we have that, and then we have our plus c, right? So, are we done? Well, not quite, because remember, our original integral was in terms of x, and we made a substitution, and there are no limits. So what we have to do is figure out what this is in terms of x. So essentially we have to reverse the substitution. But the nice thing is, to reverse the substitution, all we need to do is to use this equation and the appropriate right triangle, right? So let's do that off to the side right here. Some more side work. I told you it was a lot of side work. All right, so we have x equals 5 secant theta. Well, let's see if we have an equation like this and we want to determine what the right triangle is. There are different ways we could do it. We could divide both sides by 5, and we get that x over 5 is secant of theta. Well, we tend to work more efficiently, effectively, more accurately when you're working with sine and cosine than with some of the other ratios. So I know if I take the reciprocal of this side, it will give me cosine. If I take the reciprocal of this side, I'll get 5 over x. So 5 over x is the cosine of theta. So let's draw the right triangle, right? And it turns out it's the same right triangle that we started with that kind of led us to this. We're going to use that triangle to reverse our substitution. So cosine we know is adjacent over hypotenuse, and then if I figure out the missing side, it's the square root of x squared minus 5. And once I have this triangle along with this equation, I can figure out what the tangent of theta is, and I can figure out what theta is, right? In fact, let's write down what theta is. Using this equation, if I take arc cosine of both sides, that will leave me with theta. So arc cosine of 5 over x is equal to theta. I don't need parentheses there. I don't know why I'm writing parentheses. Right? So that can go here, right? In fact, I'm going to write it right below. So this theta will be replaced with arc cosine of 5 over x. And then how do I get the tangent? Well, look at the triangle. Tangent, we know, is opposite over adjacent. So the tangent theta, that is our root of x squared minus 5 over 5. Right? So with the same equation that we started the process and the right triangle that led us to this process, we can reverse the substitution and then get our answer in terms of x. So we have 5 times the quantity, square root of x squared minus 5 all over 5, and then minus arc cosine of 5 over x, and then plus c. So we can actually distribute the 5, and then we're left with the square root of x squared minus 5 minus 5 times arc cosine of 5 over x plus c. Right? And that's one version of the solution. Another version is we could have expressed theta in terms of arc secant. So in other words, instead of if you're comfortable working with things like secant, we could have said that, hey, this is telling me that if I take the arc secant of both sides, I could get theta, right? So another way it could be expressed is that it is theta is arc secant of x over 5. In fact, theta could be represented using any of the 6 arc trigonometric functions, right? Your inverse trig, any of the 6, because we could get a relationship for theta in terms of any of the 2 of the 3 sides of our right triangle, right? So sometimes you might see answers in terms of cosine, or inverse cosine, I should say, or inverse secant, right? Okay, so that's one example, and we can see that these are not short problems by any means. And what we're going to do is I'm going to break these examples into a series of videos, right? So we're going to end this video now, and in the next video we will do a couple more examples that illustrates using the other two equations. So we used the equation that involves secant. We will see what it looks like to use the equations that involve sine, and then there's another one that involves tangent, right? So switch on over and I'll see you now, or then, or later. See you at some point. Bye.